Okay, so from my side, audio and video is clear. Please tell me about your side. I think it's clear. Tell me everyone, from my side, audio and video is clear. So tell me about yours. Hello Sweta, good evening. Good evening everyone. Good evening guys. Good evening. So today's session is again on Bode plot, on control system. So under fast track control, we are we will discuss error using Bode plot. Okay. So we will discuss error analysis. Okay, using Bode plot, how to calculate the steady state error using Bode plot for type 1, type 0, type 2, type 2 systems. Okay, so we'll see that. But please tell me. Okay, so audio and video is clear. Okay, fine. So let's first cover the introduction part. This session will be very small. It will not be that much lengthy. Approximately you can say 15-20 minutes session. Okay, so I hope you will enjoy this session. I hope you will understand something new in this session. Okay, so let's discuss the concept. But first let's cover the introduction part. So this is my introduction. My name is Asu Jangda and I teach almost every subject. So right now it's time for the control system. Those students who are financially not that much strong, they can give the national scholarship test for GATE exam, and this test will be on, it was on 11th of June. So today itself at 12 p.m. But don't worry guys, every weekend you can attempt this test. So on the next weekend also you will get the test, and you can perform this test, get the scholarship and join BYJU'S exam prep platform, and you can start your study with us. Okay. So you have to register for it. The link is given in the description, so you can register there and you can join this platform. There is a free workshop which will be on 13th of June. It will be taken by Abhinav Negi sir at 7:30 p.m. So don't forget to register it. You can recommend this workshop to your juniors also, to your friends who want to prepare for GATE 2024. The title of the workshop is 7 Key Factors That Transform Average Student to GATE Toppers. It means you'll get some ideas, the different thing that the toppers do. So you can get those things from Abhinav Negi sir. He will advise you, he will tell you about those methods. So you can join this free workshop. Okay, now it's time for Guru Dakshina, and the Guru Dakshina is you have to subscribe our channel. If you have not subscribed it, like this session, it's important guys, and press the bell icon so that you get the notification whenever my session is live. Okay, so it's time to start the session. I told you in the title of the session is we have to calculate error, steady state error using Bode plot. Now what is steady state error? We know that for steady state error, let me tell you some basic point about steady state error, especially for unity feedback system. Okay, let's say the system is like this. This is my GS and this is the unity feedback. Okay, let's say feedback is negative. So for unity feedback system, this signal at this position, this signal is known as the actuating signal, or especially the error signal, you can say it. Okay, the error signal, because the feedback is unity. For unity feedback, this signal is known as the error signal, or you can say actuating signal. So now actuating signal itself is an error signal. Okay, whenever the feedback is unity. Now for unity feedback system, if you want to calculate the steady state error, ET steady state, then it depends on the type of the system. How to check the type of the system? You have to check the poles of GS. How many poles of the GS lies at the origin? That will tell you about the type of the system. Let's say GS is like this. Okay, for unity feedback system, let's say GS is like this, S+1 into S+2. So you can see that there is no pole at origin. There is no pole at origin. So it's a type 0. It's a type 0 system. Okay, type 0, and order is 2. So it's type 0, order 2. Okay, now let's say GS is like this, 1 over S into S+2 or S+1. So you can see that there is one pole at origin. Okay, and the total power of S is 2. It means the order is 2, but type here is 1. Okay, here the type is 1. Here the type is 1. Okay, and order is 2. Similarly, let's say GS is like this, 1 over S square into S+1, S+2, whatever. Okay, now you can see that there are 2 poles at origin. So it's type 2, order 4. Why order 4? Because the maximum power in the denominator, maximum power of S in the denominator is 4. So it's type 2 system. It's type 2 system. So depending on the type of the system, you can tell the steady state error. Now the steady state error, ET steady state, the steady state value of this error that is going into the controller, that steady state error, it can be calculated via a different method, 1 over 1 plus Kp, or 1 over Kv, or 1 over Ka. These are the formulas for steady state error. Now I don't want to go into the depth how to calculate these formulas, what are those formulas, so I don't want to go into that. But let me tell you guys, this formula is applicable if the system is type 0. And this formula for steady state error is applicable if the system is type 1. And if the system is type 2, this formula is applicable. So depending on the type of the system, we will apply different formula. For type 0, this will be the formula that we need to apply. For type 1, this will be the formula. And for type 2, this will be the formula. But let me tell you guys, this error, this steady state error for type 0 is valid for step input. For step input. It means this steady state error formula is applicable if the system is order 0 and the input is step input. Okay. For step input, you have this steady state error. For ramp input, you have this steady state error equal to 1 over Kv. And for parabolic input, now I expect that it is clear to everyone. Okay, I'm just revising you this part. I'm not telling you from where you got this these formulas. Okay, so I'm just revising you because I don't want to tell you about this thing. I want to come to Bode plot. Okay, and with the help of Bode plot, how to calculate these error, I'll tell you. Okay, so for type 2 system, the error will be finite. This is the steady state error, and it will be finite for parabolic input. Okay, for parabolic input, I told you. Okay, so for parabolic input, if the system is type 2, you'll get this finite error. For type 1 system, if the input is ramp, if the ramp input is there, if the input is increasing linearly, if the ramp input is there, then you'll get the finite error. And if the system is type 0, then for step input, you'll get the finite error. Now, what is this Kp, Kv and Ka? Kp is known as position error constant, Kv is known as velocity error constant, and Ka is known as acceleration error constant. Okay, I think everybody know that. I don't want to go into that. Okay, but let me tell you how to define Kp, how to calculate Kp. Kp is known as position error constant. Now, how to calculate Kp? Kp is limit s tends to 0 of Gs, because Hs is already 1. So this is the formula for Kp. And if the input, if the type, type of the system is, you can say 0, then it will be finite. It will be finite. Okay, it will be finite. If it is finite, then the steady state error will also be finite for type 0 system. Okay, so you have to be very careful. And especially this steady state error will be finite for step input. We have to check whenever the input is step. Remember, whenever the input is step, we will go with this steady state error. If the input is ramp, we will go with this error. When the input is parabolic, we will go with this error. Okay, so you have to be very careful about this. So I told you what is Kp. What is Kv? Velocity error constant. That will be limit s tends to 0 sgs. Okay, this is my velocity error constant, and acceleration error constant is limit s tends to 0 s square gs. Okay, this is known as Ka. Okay, I hope it is clear to everyone. Okay, so this is clear to everyone. Now the question is how to calculate these error using Bode plot, especially these error constants, because once you get these error constants, you can easily calculate the steady state error. You can easily calculate the steady state error for the specific input. Remember, okay, these steady state error will be finite for these type of input. It means, let's say input is ramp. For ramp input, the finite error will be 1 by Kv. It means you have to calculate Kv, okay, and you can get the finite error. Is it clear? For ramp input, you will get the finite error. I hope it is clear. So I told you that these are the error constants. These are the error constant, and you can calculate error using using these constants. Now the problem is how to calculate these error constants using Bode plot. Using Bode plot. Because it is necessary to calculate these. I mean, you should understand from Bode plot how to achieve these error constants. Once you get these error constants, you can easily calculate the steady state error. Okay. So let's try to understand how to calculate these error constant using Bode plot. So first of all, let's say the Bode plot is like this. Let's say the Bode plot is like this. This is the magnitude plot. Okay. This is the magnitude plot which is provided to us. Okay. So let's say it's Gj omega magnitude and Hj omega magnitude. Hj omega is 1 actually. Unity feedback is there because if nothing is mentioned by default, we have to take unity feedback. Okay. Let's say, and this is omega on log scale. On log scale, and let's call it omega 1. This frequency is omega 2. This frequency is omega 3. Okay. And let's say this height is k naught dB. In decibel, it's k naught dB. Now we know that this system is a type 0 system. How can you say that? If you want to write the transfer function, if you want to write the GSHS from this Bode plot, if you want to write the GSHS from this Bode plot, you can easily see that at omega 1, and the slope is minus 20 dB per decade. Let's say slope is also given. Minus 20 dB per decade. Now we know that if you want to write the transfer function from this Bode plot, let's say the system is minimum phase system. Okay. Now if you want to write the transfer function from this Bode diagram, then what you can do is, you know that at this point a pole will lie because the slope is decreasing. At this point a 0 will lie. It means because the slope is increasing from minus 20 dB, you are coming to 0 dB. So at this point a 0 will lie. At this point again a pole will lie. It means if you want to write the transfer function, it will be like this. If you want to write the transfer function, it will be like this. At omega 1, so s by omega 1 plus 1, it has to be in the denominator. Okay, it has to be in the denominator. This has to be in the numerator, s by omega 2, because at this point the slope is increasing. And again at this point it has to be s by omega 3. I hope it is clear. So this will be the transfer function. And obviously there must be some constant k. We have to calculate this k. How to calculate, I will tell you. So this is the transfer function of the system. Now we know that this system is type 0. We know that the system is type 0. If the system is type 0, then we know that the steady state error, it will be 1 over 1 plus kp. This will be the steady state error for step input. Okay, this will be the steady state error. It means we need to calculate kp. How to calculate kp? We know that kp will be equal to limit s tends to 0, gs, and hs is already 1. By default we are taking that unity feedback is there. So I can write kp like this. This is my kp. Now once you got this GSHS, you can easily calculate kp. And if you look at this GSHS, this is my GSHS. And if you put in this expression, if you put s equal to 0, then kp has to be equal to k. Has to be equal to this k. It means in Bode diagram, if somehow you know how to calculate this gain, k, steady state gain of the system, okay, steady state gain of the system, how to calculate this k, or DC gain you can call it, okay, how to calculate this k itself will be the kp. Now how to calculate this k? How to calculate this k? If you want to write from the Bode diagram, if you want to write the transfer function, you can write it like this. Now how to find this k? We know the pole location, we know the 0 location by directly looking at the corner points. Where the slope is increasing, it has to be in the numerator. Where the slope is decreasing, at that point it should be shown in the denominator. It means this has to be pole. This has to be pole because slope is decreasing. Okay, but at this point the slope is increasing, so it has to be 0 here. So it means we know which quantity should be written in the numerator and which quantity should be written in the denominator. But how to calculate this k? How to calculate the DC gain of the system or steady state gain of the system? Because There are two different things, but let it be like this. So let's call it DC gain for the time being. So how to calculate this K? This K can be calculated from the first line. Remember, the first line in the Bode diagram, whichever line is the first line. I mean, this is the first line now. You can see that this is the first line. The height of the first line at omega equal to 1, that is known as K. Remember this rule. It means at omega equal to 1, let's say 1 is here. Let's say omega 1 is here. So at omega equal to 1, what is the height of this first line? That height is known as this K. Now how to calculate this height? We know that at omega equal to 1, if I extrapolate this height line, because I am assuming that omega 1 and omega 2 is less than 1. You can assume anything. You can assume 1 here also. I am assuming 1 is lying here. So if 1 is lying here, wherever 1 lies, it doesn't matter. You have to look at the height of this line. If this first line is not up to this 1, you have to extrapolate it. Okay. So by extrapolating, if you can calculate the height of this first line at omega equal to 1, that height itself will become K in dB. But we want the actual value of K. So this height is K naught dB. Okay, so it means it is in dB. So we have calculated this height. It's K naught dB. It's given in the diagram. It's K naught dB. But we want this K. It means this height is the decibel value of K. It means it has to be 20 log K. Is it clear, guys? The height of the first line at omega equal to 1 is the decibel value of this K. How to calculate decibel value? 20 log K. So 20 log K is the height of the first line at omega equal to 1. So I have extrapolated it. I have calculated this height. This height is K naught dB. So I have written it's 20 log K. Now I can calculate K from here. So K will be equal to K naught by 20, and this has to be 10 raised to the power. Okay. So I have taken the anti-log. So you can calculate K like this. I hope it is clear. Once you get this K, you'll get the Kp, position error constant. It means this height itself is 20 log Kp, because we know that K is equal to Kp. So in place of this K, you can write Kp also. No? It means the height of the first line at omega equal to 1, that is known as 20 log Kp. So from there you can calculate Kp. Kp means position error constant. Once you get this Kp, you can put it here and calculate the steady state error. I hope it is clear, guys. I hope it is clear. Okay. So you can calculate the steady state error directly from here in the Bode diagram. Okay. In the Bode diagram, you can directly calculate the steady state error. But let me tell you guys, this method is valid for minimum phase system. If the system is non-minimum phase, then you can't calculate that, because in that case, if the system is non-minimum because of the right half poles, if the pole lies in the right half, I'm not saying about zeros. If let's say any pole lies in the right half, then you can't apply, you can't calculate Kp like this. This final value theorem is not applicable. Okay, this is the final value theorem. You can see that this will be the final value theorem. So you can't apply the final value theorem. You can't calculate Kp. It means the system has to be stable. Okay, the pole should not be in the right half of the S plane. So I'm assuming that the system is minimum. For minimum phase system, you can say like this. Okay, whatever the height of the first line is at omega equal to 1, that height is equal to 20 log Kp. From here you can calculate Kp, and once you get Kp, you'll get the position error constant, and you can put it here and calculate the steady state error for step input. Okay, so for step input you can easily calculate the steady state error. I hope it is clear. Now let's come to the next. If the system is not type 0, because this system is type 0, we know that there is no pole at origin. The system is type 0. Now let's come to type 1 system, because I know that for type 1 system, velocity error constant we have to calculate. Okay, for type 1 system, velocity error constant we have to calculate, and then 1 over kV is the steady state error. So how to calculate kV? Velocity error constant. How to calculate that? Let's say the Bode diagram is like this. How you will know that the system is type 1? How can you know that? It's very simple. Let's say the first line is like this. It's decreasing. The initial line is itself decreasing. Okay. And then let's take it like this only. Okay, let's say this is the Bode diagram. The Bode diagram is given like this. Okay, this is minus 20 dB per decade. The slope of this line is minus 20 dB per decade, and the slope is of this line is minus 40 dB per decade. And this point is, let's say, 0.1. Let's say this is 0.1, and the height, this height is, let's say, maybe 40 dB. Let's say this is 40 dB. Okay, this height is 40 dB. Now we want to calculate the steady state error. Now, first of all, can you tell me what is my GSHS? From this Bode diagram, can you write GSHS? Yes. This is Zj omega Hj omega. The magnitude of this in decibel is given like this. So it's a Bode plot, and I'm assuming, by default, I'm assuming that the system is minimum phase system. Now, if you want to write this GSHS from this Bode diagram, what will be the GSHS? Can you tell me, guys? From this Bode diagram, you can write GSHS. What is GSHS? Tell me, everyone. You can see that in initial line is it's decreasing itself. It's not constant now. In the previous case, it was constant. It is not constant now. It is decreasing. It means you have to write S in the denominator because the slope is minus 20. If the slope is minus 40, initial line is decreasing with the slope of minus 40, then I have to write S square. Okay, but the initial line is decreasing with slope minus 20 dB per decade, so I have to write 1S in the denominator. And this is the corner point. At this corner point, again the slope is further decreasing by minus 20 dB per decade. If the slope is further reduced, it means it will also be in the denominator. I told you, whenever the slope decreases, you have to write in the denominator. Okay, so this term, since minus 20 dB per decade further decreases at this point, so that's why I have taken S upon 0.1, S divided by 0.1 plus 1. Okay, now what about in the numerator? There is no zeros. There is no zeros. You can see that everywhere it's decreasing. I mean, this is the corner point. Only one corner point is there. At this corner point, slope is decreasing. There is no other corner point. So in numerator, you have to write K. Okay? In numerator, you have to write K. I hope it is clear, guys. So now you can see that there is one pole at origin. There is one pole at origin. It means if the initial line is decreasing with minus 20 dB per decade, it means the system is type 1. Okay? It means the system is type 1. So for type 1 system, we need to calculate velocity error constant, and velocity error constant is limit S tends to 0, S GSHS. S GSHS. This is my velocity error constant. Velocity error constant. Now how to calculate it? Let's try to calculate this K. If I apply this, so limit S tends to 0, let's see what is, so GSHS is this, K divided by S upon 0.1 plus 1. This S is cancelled, and you can see that if I put S equal to 0 here, so I will get Kp is equal to K. Again, it means this K will itself become Kp. Now how to calculate this K? Tell me, guys. How to calculate this K? In Bode diagram, if you want to write from Bode diagram to transfer function, if you are writing, how to calculate this K? If you know this K, it means you know this Kv, velocity error constant. You know this Kv. Okay? If you know this K, you know this Kv. Okay, now how to calculate this K? It's very simple. What you can do is, I told you how to calculate this K. This K can be calculated. The DC gain in a Bode diagram can be calculated using the first line. So this first line, what is the height of this first line at omega equal to 1? Okay, let's say this is omega equal to 1. Okay, so at this omega equal to 1, what is the height of this? This height in dB is known as 20 log K, because this K in decibel is 20 log K, and I told you how to calculate this K. This K can be calculated from the first line. The height of the first line in Bode diagram at omega equal to 1. If this line does not exist at omega equal to 1, you have to extrapolate it. So let's extrapolate this height. Let's extrapolate this line and calculate the height of this line at omega equal to 1. That height is 20 log K. It means 20 log kV. Okay, so this point itself, this height is 20 log kV. I hope it is clear. And from here you can calculate kV. Now what is this height, guys? What is this height? How to calculate this height? Using slope you can calculate. You know that if you are moving one decade means 10 times. If you are moving 10 times, then the height has to be decreased by 20 dB. Height has to be decreased by 20 dB. Now you can see that at point 1 the height is 40 dB. You are going 10 times forward. Okay, you are moving 10 times forward. It means 1 decade. You are moving 1 decade. It means in 1 decade 20 dB has to decrease. It means at this point the height has to be 40 minus 20. It means this has to be 20 dB. Okay, so this height has to be 20 dB. Is it clear, guys? So we found that this height is 20 dB. Is it clear, everyone? Using this slope idea, you can calculate what is the height at omega equal to 1. You should know how to calculate these heights. Now from here you can calculate kV. kV came out to be 10. Velocity error constant came out to be 10. I hope it is clear. Okay, I hope it is clear. So I got kV as 10. Once you get this kV, you can write steady state error. The steady state error will be ET steady state, especially for ramp input, that will be 1 over kV, and kV is 10, so it will be 0.1. It's easy peasy. Okay, so the steady state error will be 1. It means you have to be very careful using Bode plot. I mean, using Bode plot you can calculate, but the Bode diagram should be of GSHS only. HS has to be 1. Okay, if the Bode diagram is of for GS or GSHS, let's say, then only you can calculate this steady state, because it is defined for GS or GSHS only. Okay, but in GSHS, HS you have to take as 1. Okay, then only you can calculate. I mean, if the Bode diagram is given for closed loop transfer function TS, let's say the Bode diagram is like this, and it is given as Tj omega. Okay, and it is like this. Okay, let's say Bode diagram is given like this. Now from this diagram you can't calculate steady state error constant. Okay, or the error constant, or the steady state error, you can't calculate from there, because the problem is it's Tj omega, it's closed loop transfer function, it's not GSHS or simply GS. So you have to be very careful about this point. It has to be GSHS or GS only, because then we can take HS as 1. Okay, then only you can calculate this kV. Now let's come to type 2 system. Let's say the Bode diagram is given as, let's take a Bode diagram, and the Bode diagram is given like this. Let's say the Bode diagram is like this. It's minus 40 dB per decade, and this is minus 60 dB per decade. Okay, and this height is, let's say, 0.1. Okay, and at this point, let's say this is 60 dB. The height is 60 dB. It is given to you. The Bode diagram is given, and the Bode diagram is for GS or GJ omega. Let's say the Bode diagram is for GJ omega, and this height is in dB, and this is omega on log scale. Omega on log scale. Okay, so this is provided to us. This is given to us. Now what we need to do is we need to calculate the steady state error. Now first of all, we need to write the transfer function of this system. Obviously we can take HS as 1, so we need to write GSHS. So from this Bode diagram we can write GSHS. How to write GSHS? You can see that the first line is not constant. First line is not constant like this question. It is not constant. It is decreasing like this. It means in the denominator we have to write S square terms, because if the slope is minus 20 we have to write S. Okay, minus 20 dB per decade you have to write S, but there is double of that. It means the power has to be 2 now, S square. Okay, so in the denominator it has to be S square, and there is one corner point at point 1, so S upon point 1 plus 1. Okay, this should be in the denominator. Now there is no zeros. You can see that the slope is not increasing at any point. If the slope is increasing at any point, let's say, then that corner point has to be in the numerator. That should be represented with the zeros. But in this question, there is no increasing point. There is no corner point at which the slope is increasing. Okay, so you have to write like this. Now in numerator, you have to write K. Okay, because there is no zeros. So you have to write K. So this is my GSHS. Now how to calculate? It's a type 2 system. We know that. It's a type 2 system. And I told you for type 2 system, velocity error constant will exist. Okay, for parabolic input. We have to calculate. We know that the steady state error is equal to, what is the steady state error? It's 1 over kV. Now how to calculate this kV? KV will be limit S tends to 0 of S square GSHS. This is how we calculate KV, velocity error constant. Okay, this is how we calculate velocity error constant. Now let's try this. So if I put it here, I mean the GSHS value, S square into, tell me guys, K divided by S square into S divided by 0.1 plus 1. And remember, I have written the transfer function of this Bode diagram by assuming that the system is minimum phase system. So this method is not applicable for non-minimum phase system, remember, because for non-minimum phase system you can't apply this concept. Okay, you can't apply, you can't calculate this KV using this final value theorem. Okay, so you have to be very careful. Non-minimum phase system, especially those systems which are unstable, non-minimum phase system in which the pole is on the right half of the S-plane, there you can't apply this method. If the zeros is in the right half of the S-plane, then you can apply that. Okay, but the pole should not be in the right half of the S-plane. Okay, so I'm assuming that the system is minimum phase system. It's not applicable for non-minimum especially. Okay, so I told you that you can calculate KV like this. So if I calculate KV, this is gone, and if I put S tends to 0, then KV will be equal to K itself. Okay, KV will be equal to K itself. You can see that KV is equal to K itself. Okay, it means again this K is represented as KV. So if somehow we can calculate this K, how to calculate K? I told you many times. I have repeated this 2 times before. Now, how to calculate K? K can be calculated using the first line. The height of the first line at omega equal to 1 can be represented as K, 20 log K, actually in dB. Okay, so in dB it will become 20 log K, and 20 log K has to be equal to the height of this first line at omega equal to 1. Now you can see that omega 1 will lie somewhere further. Okay, because this is point 1. At point 1 this is terminated and the next line is started. So you have to extrapolate it. You have to extrapolate it. If 1 is lying somewhere here, then it will be very good. You can directly calculate height at 1. But if 1 is not lying on this line, so what you can do is you can extrapolate this line. You can extrapolate this line and omega equal to 1. So let's take it omega as 1. 1 will lie here. Why I'm saying that 1 will lie here? Because you know that at this point the height is 60 dB and at this point the height is 0 dB. And we know that height will decrease by 60 dB in 1 decade. In 1 decade, height will decrease by 60 dB. So from this point to this point, the height is decreased by 60 dB. It means the distance has to be 1 decade. 1 decade means 10 times. So you have reached here. This is at omega equal to 1. This point is omega equal to 1. Now at this point, we have to calculate this height. This height will be represented as 20 log K. This height, the height of this first line at omega equal to 1, that will be represented as 20 log K. And K is equal to KV. So what you can do is you can write like this, 20 log KV. Is it clear guys? 20 log KV. Okay, and this height is given as 60 dB. Oh, not 60. You have to calculate the height at this point. What is the height at this point? Tell me guys. Obviously, you know that the slope is minus 40 dB per decade. It means if you are going 1 decade, then the height has to decrease by 40 dB. And you can see that from point 1 to 1, it's 1 decade. The distance is 1 decade, 10 times. It means the distance is 1 decade. So the height has to decrease by 40 dB. At this point, the height is 60 dB. If you decrease the height by 40 dB, then at this point, the height has to be at 20 dB. Is it clear, guys? According to the slope, I have calculated the height. So this height is 20 dB. You can write it 20. Okay. And KV can be calculated as 0.1. Oh, sorry. 10. KV, you can calculate KV from here. It should be 10. I hope it is clear. Okay. So this is my KV. It's 10. I hope you got the idea. Once you get this KV, this is not KV, this is KA. Excuse me. This is acceleration error constant. Excuse me, this is acceleration error constant. Okay, so KA. I have to write KA. I have to write this K because it's a type 2 system, na? So I have to write KA. So this has to be equal to KA, acceleration error constant. So the method is same everywhere. Everywhere the method is same. I hope it is clear, guys. Once you get this KA, you can put it here and calculate the steady state error. Okay, so it's easy peasy. It's again easy peasy. So ultimately, if you are looking all the plots, if you are looking all the plots, let's say you are looking this or this or this, okay? In every case, the height of the fifth line at omega equal to 1, that can be represented as 20 log Kp or 20 log Kv or 20 log Ka. Here in type 2, it is 20 log Ka. In type 1, at omega equal to 1, the height is 20 log Kv. In type 0 system, the height of the first line at omega equal to 1 is 20 log Kp. This will become 20 log Kp and you can calculate Kp from here. Okay. So everywhere, in every Bode plot, whether the system is type 0, type 1 or type 2, the height of the first line at omega equal to 1 is represented by the error constant, the decibel value of the error constant. Okay. So you can directly apply this concept and you can calculate the error constant from there. Once you get the error constant, you can calculate the steady state error. Okay. But this method is applicable only for minimum phase system. Okay. Minimum phase system. Minimum phase system. Minimum phase system. If the system is non-minimum, then its pole should not be in the left half. Okay, pole should not be in the right half. Zeros may lie on the right half. If poles are lying on the right half, then you can't apply this method. Okay, so you have to be very careful. For non-minimum phase system, you can apply this. But for non-minimum phase system, zeros should be on the right half of the S plane. Pole cannot be, because the system should be stable. System must be stable. GSHS must be stable. Okay, GSHS has to be stable system. Then only you can apply this method. If the system is unstable, you can't apply this method. Okay, you have to be very careful. Now, there is one interesting point that I want to ask you. Let's say the system is type 2. Now, this is your homework and you can comment in the comment section. If I extrapolate this, initial line in type 2 system, what is this frequency? What is this frequency? Let's call it omega t. What is this frequency omega t? That will be equal to root Ka. It means it has to be equal to root 10. You can prove that. So it is your homework, okay, that you need to prove it. You need to prove it. Okay. If you have proved it, then you can write in the comment section, hence proved. Okay. You can write this word, hence proved. Okay. Let's see how many of you can prove this. If you extrapolate this line in second order system, this has to be root Ka. Okay. Now you have to prove it. Okay, guys. Okay. I hope it is clear. I hope it is clear. Now, there is one more interesting point that I want to tell you. If the system is type 1 order 2, like this is type 1 order 2. In type 1 order 2, there is one interesting case. And what is that interesting case? This corner point is 0.1. This corner point is 0.1. Okay, let's call it omega naught. Let's call this crossing point, the Bode plotting crossing point. I'm not saying that this is 1. Okay, let's look at the crossing point. Let's call it omega t. And if I extrapolate this, call it omega 1. Okay, call it omega 1. I extrapolate this line and the crossing point is omega 1. Now, you can say that this omega t, this omega t is the geometric mean of omega naught and omega 1. I mean, these are the direct rules that you can remember. These are the tricks that you can apply here. But for this rule, I mean, if for this to be applicable, the system has to be type 1 and order 2. The system has to be type 1 and order 2. Remember this point. If the system is type 1 order 3 or order 4, no, you can't say like this. Maybe you can say or may not be you can say. I mean, this is not valid. May be valid or may not be valid. I mean, sometimes it's valid, sometimes it's invalid. So, but for type 1 order 2, this will always be valid. For type 1 order 2, if there is no zeros, remember, okay? If there is no zeros, system is type 1 order 2. If there is no zeros, then this will be applicable. It means this has to be geometric mean of this point and this point. You can remember this point also. Okay, you have to remember this point also. Okay, so I hope you got the point. I told you some basic point, I told you some basic ideas. Okay, how to calculate the steady state error constant, these error constant, how to calculate kV, kp, ka, and the special points about some specific type of system. These special point like this omega t is the geometric mean of this, and I told you that this is root Ka. So these are applicable only for this type of systems. Okay, like this condition is applicable if the system is type 1 order 2 and there is no zeros. Okay, then only you can say like this. Okay, I hope you got the point. I hope you understood it. Okay, so it's time to stop the session, guys. I hope you enjoyed, and I hope you got the idea how to use Bode plot to calculate the steady state error. Okay, so that's all for today's session, guys, and now it's time for Guru Dakshina again. So you have to give the Guru Dakshina. Don't forget to subscribe our channel, like this session if you have not liked it, and press the bell icon so that you get the notification whenever my sessions are live. We have our mobile app also, so go to the Google Play Store, search our mobile app BYJU'S Exam Prep, install it, and you will get free lectures from there also. Okay, and you can do some practice and you can enjoy. Okay, so I'm teaching on the mobile app also, so you can do that. I want to tell you one more interesting point. That point is, today we have uploaded a video of positive feedback and negative feedback. Okay, please do watch that video. How to watch it? On our channel, on YouTube channel that you have subscribed, go to the video section. Go to the video section. In video section, you will find that lecture. You will find that video. Do watch it. Okay, on positive feedback and negative feedback. That is again very interesting video. It will help you to understand what is positive feedback, what is negative feedback. Okay, so please watch it. So that's all for today's session, guys. I hope you enjoyed. See you in the next session. Next session will be on tomorrow. So take care. Bye.